Okay, very good, excellent. So this lecture is recorded for Wednesday, October 11th, because I will give an invited talk in the conference, so I cannot meet you in person. So this you can watch this lecture during the Wednesday's class time, okay? And then we will meet on Friday, October 13th. Now, today we will continue to talk about the probability theory and the random walk and the diffusion. Before that, there's one update about the logistics. That is, for the midterm exam number 2, you can start to talk with me, discuss with me about the topics you want to dig into, you want to present, you want to make them to become the final project. Okay, and then I can help you to decide the topic, and I can also guide you to the relevant references on that topics. Okay, so it will be helpful that you talk to me now, and I help you to save the time, so that you can concentrate your efforts into the correct and appropriate topics for the project. Okay, so that will be useful for both midterm exam number 2 as well as the final project. Okay, so our midterm exam number 2 will be on October 30 and November 1st. So we have enough time to discuss about which project you want to work on, and then you also have time to read relevant materials to prepare the presentation for the midterm exam number 2. You can do it either individually or collaboratively with other classmates together. Okay, either way is fine. So every student will present for 10 to 12 minutes, and then we leave 2 to 3 minutes for questions. Okay, so it will be great, and make sure you read the excellent examples I put in the canvas. That is those were from the previous excellent students. So you can read the format, understand the format, and then follow the format. But you come up with your own new idea, okay, to develop some creative idea for the important topics. Okay, yeah, good, very good. That's all for the updated logistics, and the other logistics we will follow what we write in the slides. Okay, good. Now let's continue our discussion. So in last lecture, we talked about the derivation about the Gaussian distribution, which is the final form of the summation of many random steps, right? So today we will continue. Firstly, we will continue to derive that equation to prove central limit theory. Okay, and then after that we will step into the field of diffusion. How can we understand the diffusion, the random walk of molecule inside the bacteria or inside the mammalian cells? Okay, and we let's understand those quantitatively. Okay, now let's start the first part. So we talked about what is the Gaussian distribution. We write explicitly the mathematical form, right? This is the simplest form of Gaussian distribution. So this is the final distribution, and then this distribution has its own mean value and the standard deviation, which is the square root of variance, right? So that equals to the second order integration of probability minus mean value square, right? Mean value square. So that is variance. And then if we put this mean value mu and sigma standard deviation inside the Gaussian distribution, this appears in this format. So this has the first term, which is reversely proportional to the standard deviation, and then has the exponential term, which has minus x minus mu square divided by 2 sigma square. Sigma square is the variance, right? The square of standard deviation. Now, this term, this expression happens in many nature phenomena. And then if that nature phenomena is consists of many different steps, and then each step has its own distribution, means that each step also has its own mean and the variance. Then the Gaussian distribution can be rewrite as the sum of all the steps together. So final distribution is appearing in terms of the Gaussian function, and in its this Gaussian distribution's mean is actually equals to the sum of the mean of all those steps, all those finite steps, and then its variance actually equals to the sum of all the variance of all those steps, right? So replace this n mu1 and n sigma 1 square into the previous function, then you will get this term, right? This exactly tells us what is the central limit theory. It says that specifically it says that the sum of a large number n of independent random variables, independent of random steps, each of them have the finite mean mu1 and the finite variance sigma 1 will follow a Gaussian distribution, right? So after many times, this final Gaussian distribution has its mean is n mu1, its variance n sigma 1 squared, right? This theory is not very obvious, right? It's not very obvious, but it is hugely important. It helps people to understand the many biological process. So why it is important? Because whatever distribution for the individual steps, they can be because of different physics, different biology. But if they all follow one distribution consistently, and then it happens many times, then after enough times, our probability distribution becomes Gaussian. Those individual steps, they can be coin toss, drawn to the steps, molecular movement, or the bacteria scandals, okay? So or others can be many different distribution. But then after enough steps, the final distribution is Gaussian. And then of course the mean and the variance of this final Gaussian is linearly proportional to the mean and the variance of the single steps, right? All linearly proportional. And this linearly proportion is linearly increasing with is a function of the time, linearly increasing with the time, because as more steps happen, then more time is needed, right? So this is all when we have more time, that the n number increase, so that the mean and the variance of the final Gaussian distribution also increase. Okay, it means if like in an ink, if the central point is not moving, is 0, then it's not moving, always not moving, is 0. 0 times n is also 0. But the variance is increasing. The width of the distribution of the ink will increase, right? So that's why the ink droplet become dimmer and dimmer inside of the water. So here is a figure showing that if we quantify the trajectory of any single particle in the water, you will see they will take this Brownian motion. And then if we overlap the position of all the moment during the movement of this particle, then we will find the chance, right? We will find the probability where this particle locate at each time point. And if we draw, because the particle is coming from the center, and then if we draw radially, we draw many rings here. All the ring, each ring has the radius, that all the point within this ring, within this the ring band has the same distance with respect to the original point, right? So then if we overlap the position of all the moment that this particles stays, then we will find that they actually demonstrated the probability where those particles stays more and where this particle stays less. That probability is actually the Gaussian distribution. So that is after many times steps, they follow this Gaussian distribution. And then they will gradually increasing their variance, right? So this is the central limit theory. This is a very important principle. Now, what we just discussed is one kind of interpretation, to understand the central limit theory, right? We also discussed another type of interpretation in the previous lecture. We said that the final probability P is actually equal to the convolution of all the steps together. You have n numbers of steps. All these steps convolute with each other one by one, following the time sequence, right? We talked about that. So if we convolute a function that is the probability distribution of that step, okay, and then we convolute that function with itself for enough time, for sufficient time, many times, it actually starts to look like Gaussian. Okay, so this is what we discussed last time when we derive, when we talk about the baby step, right? And we derived that. Now, to prove whether the central limit theory is correct or not, we can use mathematical way to prove this statement. Once this statement is proved, then that means central limit theory is accurate. Okay, so let's continue last lecture's derivation to prove this mathematically. So to prove the central limit theory, in last lecture, remember we derived the first part. There we involved in a new mathematical form. It's called Fourier transform. Okay, so let's briefly discuss what is Fourier transform. Then you can use it you can understand it better in the further derivation. Now, Fourier transform actually is a very useful way to decompose it, okay, separate one function into many components, and all those components actually are theoretical function. All of them theoretical function, sine function, cosine function, okay. And then the way to separate them actually is to make them to have a different frequency in the periodicity. Okay, so the basic theory of Fourier function is for any function that is periodical, it actually can be separated into many other periodical functions with each one with different frequency, and then add those functions together can compose any periodical function with very strange shape. But they can all, no matter how irregular the function is, it can always be composed by the sine and cosine function with different frequency. Okay, that is the theory, and it was originally derived in the heat transfer field. Okay, and it works well, and then it becomes very popular in the, not only popular but also very important in the electrical engineering signaling processing. Okay, and then because signal processing is a very general method for many other engineering applications, so then Fourier transform find this wide, broad application in many engineering fields, okay, including bioengineering. Okay, so general form of Fourier transform is if we have a function of fk, okay, fk, we can multiply it with exponential 2 pi I kx. I is the exponential. I is exponential. Okay, 2 pi I kx. Here the reason people put the e to the exponential I constant is because ei something actually equals to cosine something plus I sine something, right? If it's ei theta, is equal to cosine theta plus I sine theta. So it gives it actually separate into two periodic functions. And then depending on the theta, it gives different frequency. And then this different frequency, actually, if they multiply with the fk, and then do the integration, sine theta and cosine theta have a different frequency. They are orthogonal to each other. When they have different frequency, they multiply together, do the integration from minus infinity to positive infinity, they will become zero. Only the function sine and cosine function have the same frequency. They add together, they multiply together, they have the square. Then with the integration, they will not vanish. Okay. So then in this way, you can actually, by multiply the exponential term, you can convert a function from the time domain to the frequency domain. And then you can also do the reverse. So times e times minus 2 pi ikx. Okay. So that then can convert time domain into frequency domain, and or convert the frequency domain to the time domain. Okay. So you can do this transfer. So the top two function I show here actually is the analytical formula for the Fourier transform for any function. Okay. K and x, actually K can be the frequency, x can be the time, and all can be the time. That is in time, in terms of time, right? You can also do it in the spatial frequency. X is a space location. K is a spatial frequency, like in a grating, right? The grating have different density of the lines there, right? That's a spatial frequency. So that's the same idea. Now, here's just one example showing that a periodic function in red color. So this is the periodic function. This function is what we measured in the lab. When you have this function, you measure it and you find it in the oscilloscope or other devices. You find actually it's periodic going, but it's very irregular. Okay, so here is one. Here, yeah. So it happens again. Okay, and then this actually is the magnitude versus the time. Okay, now by doing this Fourier function, by doing this integration, you actually can separate this curve into three components. You will find that they actually have three components. They are actually the sine function. They can be the sine function. One is a lower frequency, this one. Another one is intermediate frequency. Another one is high frequency, right? This purple one is high frequency. And then because of they have a different frequency, actually by doing this Fourier transfer, you find you can find a frequency. You can convert this to a frequency domain, magnitude versus frequency. So it tells us this frequency, low frequency, and what's the magnitude. This peak actually indicating this equation, this curve. Another one here, higher frequency, actually indicating this one. Even higher is actually indicating this one. Okay, so this curve is coming from the Fourier transform. It tells us the frequency information. Okay, frequency information. With this frequency information, and also they have magnitude, you can also convert it back to the time information. So basically, Fourier transform is telling us the event in the time domain and the embedded frequency of those events. That if we extract out, we will get to the frequency domain. Okay, so that's the very useful. That's a very useful transfer to tell us how many components are inside one event. That's very useful. So there are already many function has been analyzed very thoroughly. People knows what is the Fourier transform of one function. What is the inverse Fourier transform of one function? People already knows that. Okay, so here I show a few particular examples. So here is one. Here I show 4 examples. On the first column is actually in the time domain. Okay, any signal st, t is time domain, and the second column is in the frequency domain. That is the Fourier transfer. Okay, after Fourier transfer. So first function you can see that's a cosine wave. That's a cosine wave. So this is the time domain, right? Cosine magnitude of variation as a function of the time. Now, if we take the frequency of it, we will find that there's only one frequency. This one only contains one frequency. That is actually this value. It's a delta function, only one value, right? It's delta function, only one frequency. So now we know Fourier transfer of a sine or cosine, which has only one frequency curve, they actually, after the Fourier transfer, they become delta function. Okay, and then another several is a sinc function. This function, if we Fourier transfer it, it actually tells us all the frequency is at a small region. No, here is actually 0. Here is a positive side. This is a negative side. So in the small region, they have many frequencies combined together. They have the same magnitude. Okay, so those many frequencies, sine, cosine function added together, it will give this. Okay. Also, interestingly, Gaussian distribution. If you do the Fourier transfer, it will give you Gaussian again. Okay. This is very unique, very useful. And finally, is a double exponential. So each one is exponentially decayed. Double exponential after the Fourier transfer, it gives a Lorentz distribution. Okay, so those are very commonly used method. Here, actually, one thing very interesting is this is a time, right? This is time. If you see the function here with the any function in a time domain, if they have some distribution here, they have a finite variance. Then you have finite variance. Then if you convert it into the Fourier domain, in the frequency domain, the frequency also is finite. Frequency is also finite. Means if you go to large frequency, large W, or WIC is a frequency. Sometimes people use K, okay, to show the frequency. But what I'm saying is that if this is finite, then Fourier transfer of this function at a large frequency, they actually equal to 0. Only have the small frequency components here. Okay, so it's a small frequency components. So this factor is very useful. So once you know the relationship of those finite variant function, they are corresponding Fourier transfer function have only non-zero value at the small frequency region. Then when you do the calculation, the large frequency region, you can ignore that. They don't need to be counted. Okay, so this we will use this factor in a derivation as well. Now there are more functions also be calculated already. So here actually I show about 30 different functions. They all are available in the mathematical books. We have the time domain function, right? So time domain function, and then we have the frequency domain function. So here are all the time domain one, and then after Fourier transfer, they become free in the frequency domain. They have a different function. Here also time domain to the frequency domain. Okay? Here as well. Here, so on the top is actually simple question, simple functions. But if we have for the more complex functions, you can also convert them to the Fourier components. Okay. Now with this, we can start to continue last lecture's derivation. So in last lecture, we talked about how to prove central limit theory by the factor that convolute one distribution by itself for many times, it will become Gaussian distribution, right? We want to prove that. So to prove that, firstly, we know that we know that like a BB that we have derived that when the BB take 2 steps, if they take 2 steps, then the final distribution after these 2 steps equal to P2, right? P2 that equals to the integral of ds1, integral ds2, and W for the 2 steps their distribution times delta function. X is the final position, x minus s1 plus s2, right? So we discussed this function several times. This is the final distribution of that BV after 2 steps. And then because the delta function itself can be written in terms of the integral, right? So this one can be written in this way. We discussed about this in last lecture. Then this term can be written in 3 components. Then we can actually add these 3 components into this delta function here, into here. Then we get a P2 in a little bit long expression. But this long expression is very useful. It contains 3 integrals. Then we can group them together. Here, I group them together in terms of dk, ds1, and ds2. You will see 3 different color, 2 different color. One is orange, 2 are blue, right? So when you look at the 2 blue one, you will find actually this function actually is the Fourier transfer IKS1. This is actually Fourier transfer for W. Fourier transfer for W. Second one is actually also the Fourier transfer for W. Only difference is their variable is different, S1 and S2. Okay, and then this orange one is also really interesting. It's actually the inverse Fourier transfer for this blue one. Okay, and then as we said, this P2 actually equal to the convolution of 2 terms, right? So what does this mean? This means the convolution of 2 function actually equals to the inverse Fourier transfer of the Fourier transfer of each, and then multiply together. Okay, this actually tells this interesting thing. So that means if we have a function P2, we want to do the convolution of it. Okay, we want to do convolution of 2 function W. We actually don't need to worry about that complicated expression of a convolution. We can actually take this each function, do the Fourier transfer for each, and then multiply them together, mathematically multiply together, and then for that product we do its inverse Fourier transfer. Okay, then it will equal to the convolution of that 2 functions, right? So this is what is shown by those mathematical factors. Okay. Now this actually is can be also written as if a fx function equals to this 2 convolution, then in fact fx's Fourier transfer equals to Fourier transfer for each function g and h times together, multiply together. Okay, and then if we do our inverse Fourier transfer of fk, then it will get back to fx, right? So here this top wave symbol actually indicates the Fourier transfer. Okay, so this is existing in many books, and this is very useful because it converts convolution calculation into a very tractable operation like Fourier transfer and mathematical multiplication. Then we can easily find out the convolution. Okay. Now, why we need to know this is because our goal is to calculate many of those convolution together, many of them convoluted together. We want to calculate its final results, whether that is a Gaussian or not, right? That's why. But that is very difficult to do. So by knowing this relationship, we can take a Fourier transfer for all those functions. They are the same function for us, right? Each step is the same, and then we multiply the Fourier transfer for all those functions together, all of them together, and then do the inverse Fourier transfer. That will give us, and then we check whether that final results is a Gaussian distribution or not. Right? If yes, then it's proved the central limit theory, right? So any small function, any finite function, if you convolute them for many times, it actually gives a Gaussian distribution. Right? Now let's do that. So for our case, we have to convolute the distribution of each step of n steps, right? Each distribution of n steps, and then, but it's difficult. So we will work in the Fourier domain, in the frequency domain. So the Fourier transfer for all those n steps, after n steps, Fourier transfer all of them actually is for each step is W, right? W, K. W take the Fourier transfer with this wave top. We take we do this Fourier transfer and then multiply with another Fourier transfer of W function, and then multiply many of them. J change from 1 to n, right? So then this is the multiplication symbol. So many multiply together. That will equal to the Fourier transfer of final results, right? So let's firstly calculate this, and then we can convert them back to the final results. And then our goal is to find out the PK, right? PK. Now, because all the W is the same for us, then this multiplication actually gives the Fourier transfer of the Fourier transfer of the W to the power of n, right? To the power of n. Now, as we just said, the one property of a function that has the finite variance, because we just said that here we can directly use that, because this WS has a finite variance, right? Each step it cannot be infinite. It's actually the measurable variance. Then the Fourier transfer of this guy actually goes to zero if the frequency k gets to very large. Your frequency k is very large, right? So that means for those value, if the k is very large, then this term is a finite, small, and then it times n times, then this term becomes very small. Then it becomes zero, okay? Becomes zero and decrease very quickly, becomes zero. So this k actually has to be small enough. If k cannot be large, if it's large, then it decreases to zero. So k has to be small. Now we can actually let the k equal to zero. We can let it the k equal to zero, because this n is very large. A little bit k will let the value quickly decrease to zero. So we go to the extreme point, let the k equal to zero. Then definitely we have a finite value, even with the n number multiplication. We can still have a finite value, right? So then, if then we only consider k equal to zero condition, okay, then we can actually expand this term by the Taylor expansion. We can see more terms, and then by doing Taylor expansion, we can actually remove the high order terms to even simplify this formula, right? So now, if we do this, we already know the Fourier transfer of this term, of this W function, actually equals to WS. This we are really familiar, right? S is a step. Right? Remember in the very beginning, we use S to know the step. So this is actually probability distribution for the step. And then this distribution times EIKS times DS to the integration. That is the Fourier transfer of WS, okay? And then K is actually the component to be found out in the frequency domain. So now with WK, the Fourier transfer equal to this term. Now this term, because we set K equal to zero, then we actually can expand this exponential term at the K equal to zero and very small, little bit amount, K little bit larger than zero, okay, little bit larger. And then we can expand this E to the IKX to the mathematical term like this, okay? So this exponential can be written as I plus the components there, which is this term, and then minus 1 over 2, and then actually it's a plus 1 over 2, that the term is square, because we have an I here. I square equal to minus 1. So then we have minus 1 over 2 k square s square, right? So this is a standard Taylor expansion of our exponential equation. We have this term. And then they also have a third term. This is actually the factories. You have the third term, fourth term. They are actually contains many higher order k, but k equal close to zero. So those terms can be eliminated, right? So we only take 3 terms. Now these 3 terms, they add together. We can actually multiply them respectively to the WS and then take the integration. First term, take the integration is WS ds integration that is equal to 1, right? Probability equal to 1. Second term is WIKS times ds, and S is the first order, right? Then IK can be taken out. WS ds actually doing the integration equal to mu. That's mu. Then we get IK mu, right? And then second term, third term, minus 1 divided by 2 k squared. This term, S squared WS integration equals to second orders. This term is mean value, right? This term's mean value. Okay. Now, that's very good. Now, with this WK, we can actually write it in terms of this WK. What we will have is actually WK the K is n power, WK times, right? We will do multiply, we will calculate this and then do the reverse Fourier transfer, right? Now this term, we actually we also can expand this. We can add this term, this express term inside, and then expand it. However, when we expand it, there's a mathematical trick. People usually don't expand it directly. Expand it. We actually use this guy, put it into the log, the nature logarithm, okay, and then we can expand, because when it's in the nature log has its own Taylor expansion. We can use that, and then after that we can add this term into the exponential, right? E to the power log something actually equal to that term, right? So let's expand the log term first, and then we can put the exponential back. Okay? This actually is also called a cumulative expansion. It's a very useful trick for the sharply varying function, okay, which exactly matches our current condition. Okay, so now let's expand this term. So this term, log line, nature logarithm line equal to this guy, and then this guy we can take the, here you have n, right? So this n can be removed to here, to the beginning, right? Then we have n log this term, and then this term we know it. This term we already derived it. It equals to these three terms. And then here we know k is close to 0, and this when the k, mu, and the s square mean all are constant. Only k is the variable here. Then we can actually this term actually is it can also be expanded by the Taylor expansion. Use this formula, log 1 plus y. This term has this expression can be Taylor expanded when the y is small. It equal to y minus 1 over 2 y squared, and then plus high order term. And those can be eliminated because y is so small. Here we can treat this one as the y, right? Then this log, this whole thing becomes n take at the beginning, at the front, and then this log for this term can be equals to the y is this term, plus y is minus 1 over 2 y squared. Y squared is actually this square, okay, this term, this square. When you do this, actually you will find the k will increase k cube term, because will k times k squared in the square, and then another third term is the k fourth order. All those terms can be removed because they are too high order. Only this term can be remained there. Then is ik mu square times ik mu square, and then the minus 1 over 2. Then is minus 1 over k square mu square. Okay. Actually, it's plus. This is a plus because I square is minus 1. I can change that. This is a plus. Then this finally two term. Actually, if this is a plus, then we extract this two term. Then it's 1 over k square times s square mean minus mu square. That means there's a s mean square, right? That term gives the variance. Is a delta s square, mean square displacement, MSD, right? Delta s square term. Then that means that finally this one give us this, and then this one we can put it on top of exponential, as we just mentioned, right? Then it becomes this term. The Fourier transform of pk actually equal to e to the power of this. Okay, e to the power of this. Now this one actually, then we do a reverse the Fourier transform for this guy. So this term we do the reverse Fourier transform, then times the e to the power minus ikx, and do the integration 1 over 2 pi. Then put this also is exponential term, then two exponential term added together. Actually is this exponential times this exponential. Do the integration, right? This one we will not have time to calculate it directly. However, this actually is a very standard Gaussian integral in the mathematics books. If you check mathematics books, this integration has direct solution with those parameters inside. And then that once you solve it, it will yield this formula. It will equals to 1 over square root 2 pi n sigma square. Sigma square actually is delta s square. This is the variance of each step. Right? And then exponential minus x minus n mu. Mu is here, this value. Mean value of each step. Okay? And then square root divided by 2n delta s square. This delta s square mean actually is the sigma square. Okay? So this actually shows what is the central limit theory. It already tells us this central limit theory. Okay? So this tells us that for any small steps, if we accumulate them for enough time or do the convolution of itself enough time, we eventually get this distribution, get this Gaussian distribution. Okay? So that's what we derived, we proved for the central limit theory. Then we can use it directly. Okay? Very good, very good. Now, after this, after those mathematical brainstorm, we now complete the Brownian motion probability part. Right now, in our class, we are actually we can start to talk about diffusion, correlation, kinetics now. Okay, those are very interesting topics as well. Now, firstly, let's look at the diffusion. So, consider for diffusion, we have a particle, a fluorescent beads diffusing in the solution. If we want to categorize its property, we actually can divide that path into short time steps, many steps, right? This we already know. And each step has the length delta t, the time is delta t. Then for the total t, we actually have n equals to t divided by delta t, right? So each delta t, in fact, each delta t, you can further think each delta t also is composed of a vast number of even smaller steps. However, if we, based on the central limit theory, we can know that if we get the same statistical properties, of the motion for any delta t, this delta t, if this t is long enough compared to the momentum relaxation time of the particle, means, what does this mean? This means if we ignore the detailed mechanics contact between the particles, to let the detailed mechanics contact to be included in all the delta t, okay? Means within every delta t, you have many of those mechanical bumping and relaxation. Then it means each delta t has enough number of small t. They all contain all those mechanical events. Okay, if that's the case, that each step delta t actually can be considered as a step that can be equal to next delta t. Okay, the event that happened within this delta t are equivalent. They are statistical equivalent. Okay. Now, for each step, each delta t, we can write their step size, the mean square displacement delta s square, equal to 2 dt. This is what we derived, right? This is what we derived, and we we assume at that time when we derive that, we assume we are in a 1D condition, right? So that's why we have 2D, right? 2D. If for the in the formula it's 2D delta t. If in a two-dimensional field, then it's 4D. Three-dimensional field is 3D. Right? That is just the convention. So this constant is just to let people know which dimensionality we are thinking about. Okay. So within those delta t step, we have this formula. Okay. And then here, capital D is called diffusion coefficient. By measuring this delta S square as a function of the t, delta t, we can measure their D. And then this diffusion coefficient actually tells people tells people the property of the particle and the property of the surrounding the viscous liquid. Okay, and the D describes how wiggly the motion is, and this D and it can be theoretically calculated. Right, the unit of the D is the length squared divided by T. So this T is length squared, is T, right? And we already mentioned that this is slower because this is a random process. It's slower than the processive motion. If there is a motion that with a constant speed in one direction, then the delta S squared equals to delta T squared. Right? And also here the factor 2, coefficient 2 is just for the convention. Okay. Now, if we have those delta S, those steps accumulated together, we have many of them. Then the final, based on the central limit theory, the final position variance after the n steps actually is a linear proportional to each step delta S squared, right? Then it equals to 2dn delta t, because delta S squared mean equal to that value. And then here n times delta t gives us the t, right? So then in the absence of external force, such as in the nature, they have flow. There are constant flow ongoing that actually will move the particle away. Then the mean position of the particle will shift. Right? If there are no external force, no shear force, no flow, then the average position of the particle will not move if you do it many times. But the distribution for that particle actually will show a distribution, and the trajectory actually follows a Brownian particle, Brownian motion. Okay, and after n steps, the origin still is x0 equal to 0, still at the point, and the distribution function can be written in terms of the Gaussian distribution, and this we already seen before. Here, the new thing is this n sigma 1 square, n mu square, it can be replaced by the time now. You can put the time in now. So as a function of the time, this function, this Gaussian function can also change. Right? And then that is because this n is changing. This n value can change. And then for the final, based on this function, for the final variance, delta S squared actually equal to 2dt. This tells us in the experiment, if you want to measure diffusion coefficient in any liquid, you can actually add a particle in, measure its mean square displacement here, and then corresponding time, and then you can calculate this D, right? By already know what's it's 1D or 2D, right? So this is actually one of the most important equations that we will use in the calculation. That is all for the 1D condition, one-dimension condition. For the two-dimension condition, the probability is orthogonal. In the x direction, you have a probability. Y direction, you also have a probability. And then the final probability, actually, final position, okay, probability of the position. Final position is a delta R squared, take the mean. Delta R squared mean actually equal to delta X squared mean plus delta Y squared mean. So then each direction, you have a 2dt. Then 2dt plus 2dt, we get a 4dt, right? So for a drunk person who is walking on the ground, if you check the foot printer of that person, they actually follow this 4dt probability. If it's a drunk, as we said, it's a drunk bird, it's flying on a space, and then you take a picture of the bird, you will find that its position delta r square is actually delta x square plus delta y square plus delta z square, 3 orthogonal direction, and then equal to 6 dt. Then based on that, you can also calculate that is not diffusion. That actually is the random process, the strength of the bird during the swimming, the corresponding property values here, right? So all these are very important. Now, yeah, and that for the 2D condition actually follows this diagram. Okay? Follows this diagram. In fact, this diagram, if those particles are moving in the liquid, if the liquid is deeper, it's not shallow, this actually also close to the 3D condition. So you need to consider the experimental conditions here to choose appropriate function to use in the calculation. Okay. Now, with all those in mind, now we can understand how the protein move inside the biological entity. For example, we can understand how much time it takes for one protein to travel inside the single bacteria. So for example, for the single bacteria, the size usually is 1 micrometer, right? Here you see the 1 micrometer, here is the value, 1 micrometer. So this bacteria, because inside of bacteria, they don't have motor protein, as we said. So then any movement of the protein, once the protein is translated from the RNA, start to be able to be used, then it need to traffic to the destination by the diffusion. And in the bacteria body liquid, in the cytoplasm, cytosol, the typical diffusion coefficient is 0.25 micrometer square per second. This is the typical for the bacteria's liquid. In that case, for 1 microsecond, how long it takes for the protein to travel from one end of bacteria to the another end? That is equal to delta S square, right? Delta S square equal to 2 dt, right? So delta S square is 1 micro square is 1. And then here, 2 dt, 2d is 0.5. And then t should also be equal to 2. 0.5 times 2 is 1. So then it's 2 seconds. 2 seconds. So if 2 seconds times 2d equal to 1 micron square. Okay. So any protein, once they are generated in the bacteria, it will take about 2 seconds to travel to the destination. Here we are talking about the maximum destination. If they are smaller, the distance is smaller than 1 micrometer, then you can get it quicker. Then it's good. This 1 or 2 seconds time scale is actually good. It's efficient. But if the cell increase the size 10 times, so this is 1 micron. If you make it to be 10 micron, then how much time it needs? Then its situation is different. Then it's a delta x square mean. It is a 10 micrometer square. That's a 100 micrometer square. And then 2d 0.5 times t. 2d times t. That is 200 seconds, right? 200 seconds times 0.5 equals to 100. So then the 10 times of change of distance corresponding to 100 times change of the time. So 200 seconds, about more than 3 minutes now. More than 3 minutes. That's a very long time for a protein. Then the cell will not be able to get enough protein efficiently to work, right? Here we are just talking about 10 micrometer. But you know, as we showed in the previous picture, for the common mammalian cell, the size is 20 micrometer. And even for the neuron, they can be meters long, neuron, right? Then this time become very large. So then they must develop a new method to transport the protein, right? That will be our topic in the next lecture, okay? So very good, very good. So I will see you guys Friday.